Hello there, this is Pre-Calculus 30. This is Chapter 8 Practice Test, Chapter 8. And we are talking about logarithms, exponentials here in Chapter 8. This is some more practice, okay? There's the review video that I did, and this is just more practice for your test here coming up, okay? So what I'm going to do is talk about graphing first. And so this question here is number 1 in your practice test in your textbook, McGraw-Hill Ryerson Pre-Calculus. Pre-Calculus 12. All right, and so it says this: which graph represents the inverse of y equals 1/4 to the power of x? Now, there's two different ways you could look at this. If you like envisioning this graph and then reversing x and y and finding the reflection about the y equals x line, that's a great way to do that. Or you could think about this as the log, right? The inverse of an exponential is the log. And so let's do in black here, log of x. So y is equal log of x base, the base that's in this exponential, base 1/4. So that's going to be your equation of your inverse. And again, that's going to be the reflection about the y equals x line. So here's two different ways you can look at this. First way, looking at this graph first. This is an exponential and the base is between 0 and 1. So it kind of comes down like this, passes through 1 and goes like this. That's what this graph does right here. So you're going to want to look for a graph that reflects about this y equals x line, right? Because inverse means reverse x and y. And so your graph here, this blue graph right here in A is not a reflection about this line. Okay, we're looking for a graph that kind of does this and passes through this same point. This is 0, 1, so it's going to be 1, 0, and it's going to kind of come down here like this. So we're looking for something like this, and my eyes are going over to D here, right here. That could be possible. Now, that's one way, and of course D is the answer. So you could do that and graph this and then flip it. Okay. But you could look at the log as well. So if you look at the log equation, if you had, let's say I'm going to try and find out what x and y are, 1 point on this log graph. I would say 1/4 to the power of something equals this. So let's go 1/4 to the power of 2. Okay, equals what? Well, that's going to be 1/16. No, sorry, 1/4 to the power of 2 gives us 1/16. Okay. So that means that x is 1/16, and y is 2. Okay, so we're looking for this point on the graph. So that's another way you could do this. So 1/16 and 2. Nope, not here. See? So this one's out. 1/16 and then 2. Oh, obviously not. That one's out. 1/16, really small here, and then 2. Not this one either. 1/16 and 2. Whoa. There it is, right there. Okay, another way you can do that. Just 1 point, and in this case, 1 point's all we need. It matches up real well. Okay, so that's looking at the graphs. If you don't have a graphing calculator, just to plug that in, whatever, that's how you can take a look at that. Okay, here's question number 3, and question number 3 says, what effect on the graph of this, y equals log of x base 3, does the transformations looking like this have on this graph? So what is this? Well, what we have here is two things, right? I see two things. I see a value here that's in with the x, and I see this big root sign, so we got to deal with both of those. So I'm going to rewrite this as log base 3 of x plus 7 to the power of 1/2. So remember that a radical, or root sign, square root sign, can be written as the power of 1/2. Okay, so that helps. I see this and I see this. Now this power, because we've learned about the properties of logs, can also be written. See, this exponent right here, that's not in the parameters. If you look at y equals a, right, a log of b x minus h plus k, whatever, there's no exponent, right? There's no provision for an exponent there, so this doesn't help us. What does that mean? Logs, right, we can rewrite this, and that's really going to help us. So that 1/2 comes down here, doesn't it? Okay. Right. So now that we have this, you see, we have a and we have h. So we can see A and H. So this is obviously a compression, vertical compression, or a vertical stretch of 1/2. And we have a horizontal change of, if this is a plus, that goes left 7 units. And 7 units left. So we got B here for number 3. All right. Yeah, I'm kind of going backwards here, I guess. Number 2. I wasn't going to do number 2, but I saw this and I thought, well, this is actually pretty tricky. So I want to highlight this, because if you run into this, this is really tricky. This negative right here, okay? Now, when you are, what happened there? When you are changing the form of a log into an exponential, what do you deal with? You deal with the base, h, you deal with this right here, and you deal with this. Notice how we don't touch this at all. That means nothing when we, so how do we account for this? Okay, so what you have to do, you first have to divide both sides by -1 to get it over here, okay? Because then it's going to be actually included in the way we can transform this. See that this should be positive. That should be positive, because we're going to miss a negative. So what this becomes now is h to the power of -k equals 5. H to the power of -k equals 5, which is the same as 1 over h to the power of k equals 5, which is the same as h to the power of k. If you take the inverse of both sides, which you can totally do, then this is 1/5. Okay, and there we go. We got C there. That's a tricky one. So notice that this is out of place right here. You got to do something with that. So divide both sides by a negative, or multiply, however you want to view that. Okay. All right. For number 4 here, now we're moving away from graphing. Obviously, now we're getting into the algebra. This one here, if you see this on your test, there's 2 different ways you could do this. Really, 2 different ways you could look at this. You could look at this and say, hey, we're dividing inside a logarithm, so that means, because of the properties there, I could subtract the logs of the top and the bottom. So you could go like this. You could go log of x to the p base 3 minus log of x to the q base 3, right? You could do that. You could also move these exponents down to the front. So you have p log x base 3 minus q log x base 3. Wonderful. So these are just all using properties here. Notice now I have this as a common factor. Okay. So if I take that out, log of x base 3, I'm left with p minus q. So that's really p minus q times log x base 3, and I see that right here. Okay. Here's the other way of doing that. Here's the other way. So again, properties. Oh, notice that in here, because this is the same base of x, we could actually do this. Log of, this is going to be x to the power of p minus q. You see that? Same bases, you can subtract exponents. And now, because of the properties of logarithms, I can bring this down to the front, and we have p minus q times log of x base 3, and you get there pretty quick. So either way you look at it, doesn't matter. Here we have to do a couple steps before this simplification. Here we just have to do one, depends on how you look at it. Either way you get to the same answer. All right, number 5. Oh, this one's great too. I love this one. Looks so tricky, but it's actually not that bad. So they give you this. They say if x equals log of 3 base 2, then this can be expressed as an algebraic expression in terms of x as what? And I know what you're thinking. You've probably never seen a question like this before. You're thinking, how do I go about doing this? Well, what you want to do is, remember from chapter 6, when we took a look at proving identities, right? Take the complicated side and reword it or rewrite it in a different way, and then see what emerges. Okay, so I'm going to take this right here. It looks pretty complicated. I'm going to say, okay, what do I know about this? How can I rewrite this in a different way? Maybe something's going to jump out at me. And of course, I would say, okay, this is 8 times square root of 3, so I could add logs, right? Log of 8 base 2 plus log of root 3 base 2. Okay, so right away, look at this. That's just a regular old number, right? 2 to the power of what gives me 8? That equals 3. So right away, we've already started to simplify this. Now, what can I do over here? Got some other properties in mind? Yep. This root could be a power of 1/2. Okay, that's great. Oh, this 1/2 could also be a coefficient now. Oh, nice. So guess what? We have this 1/2 log of 3 base 2. So we're just simplifying. And now you look and say, okay, I have no idea what to do now. But then you see, hey, remember what they gave me at the very beginning? That log of 3 base 2 equals x. So if I could find a log of 3 base 2 somewhere in my simplification, wow, right here. Sorry, am I being too dramatic? This is just so exciting to me. See, this equals x. Look at that. So what do I have? I have 3 plus 1/2 x, or 1/2 x plus 3, and I think I see that right here. I see it right there. Okay, so that's number 5. All right, so take something complicated, just start to whittle away at it. Just start to break it down and see what emerges. Okay, now we've got some tougher questions in here. I'm not going to do all of them. I'm just going to do a few. I'm going to point out a couple things for you. The first thing I want you to make sure that you know is this. If you ever see an equation with a log on one side and a regular old number on the other, you got to know what to do. This is easy. You rewrite this as an exponential. You get rid of that log altogether and you rewrite it as an exponential. So I start with this base of 9. Okay, so here's a 9 to the power of -2 equals whatever is inside here, right? 9 to the -2 equals this. You do a little circle. So that is x. Okay, well, this is 1 over 9 squared equals x. That's 1 over 81. Okay. Okay, equals. I don't know why my equal sign is going like that. Equals x. Okay. All right. Okay, good. Now the next one here, let's do b. Again, a logarithm on one side and a regular old number on the other. Boom, exponential. So b, x to the power of 3 over 2 equals 125. 125. Okay, so now you're saying, how do I solve for x now? Remember what you do with an exponential. Okay, is this over 2 here, this 2 in the denominator of a exponent? That's the same as square root, right? Okay, so you could square both sides to get rid of this. Or think about this way. Square both sides like this, and then when you take a power raised to a power, you multiply. So 3 over 2 times 2, those are going to cancel. So this just becomes x cubed is 125 squared. 125 is, what is that? Some crazy 15,000 something. What is it? I think I did it over here already. I've run through some of this already. Where am I? Oh gosh. Well, this isn't working out very well, is it? 15,625. See that? Yeah, 15,625. There you go. I did this before. So x cubed equals 15,625. And yeah, so now we take the cube root of both sides, cube root, and that should be, I believe it's 25, if I remember correctly. 25 cubed. Okay. Now, boy, what to do? Again, log, number, exponential. And actually, let's do C, because C is probably a good one. D is pretty tough. It talks about the it requires the change of base formula, which we don't work with a lot in this chapter, so I'm going to save that one. I don't want to totally freak you out on D. Maybe I'll do a separate video for D to show you that one, but I'm not going to include it in this review. But I will go with C here, because this has got log. My goodness, what are they trying to do to us, right? Okay, no problem, actually. So watch this. Log of 3, I'll just rewrite it. Log of 125 base x. Sorry. Okay, so I do have a log on one side and I have a number on the other. So conventional wisdom here would say that we should write this as an exponential, and we are going to. Even though we have another log in here, let's just do what we can. So 3 to the 1 equals all this. 3 to the 1 equals log of 125 base x. That's no big deal at all, because I just do that same thing again. I have a log on one side, I have a number on the other, do exponential. So x to the power of 3 equals 125. Cube root both sides, boom. I get x equals 5. Okay? Alright, so again, look for those if you have a log on one side and no log on the other. Probably exponential is the way you're going to go. All right. I think this is the last question I have on this practice. We don't do a lot of word problems here on my videos. I just work on skills a lot, but I want to talk to you about this type of question in case you run into this, because it's important that you can figure this out. And actually, when I did this before, the way I did it was totally different than the solution manual. So if you have a solution manual, or if your teacher does this a little bit different way, it's okay if you do it a different way. I noticed that this was mentioned in one of the key ideas of one of the sections. So this is what I went with. And I'm like, yeah, I'm going to try it this way, even though it's different than another way. So this is how I looked at this, okay? So let's read through quickly. Ethanol is a high-octane renewable fuel derived from crops such as corn and wheat. Through a process of fermentation, yeast cells duplicate in a bioreactor and convert carbohydrates into ethanol. Researchers start with a yeast cell concentration of 4 grams per liter in a bioreactor. 8 hours later, the yeast cell concentration is this. So if we stop there right now, we're starting with 4 grams, and there's some kind of rate of change, right? There's a rate factor, and every time this rate factor is applied, it gets bigger and bigger, and after 8 cycles of this rate change, we're at 12.8. So I'm looking at it like this. I have an initial quantity of 4. My change factor, I actually don't know what that is, but I know that 8 changes later, I get 12.8. So that's the way I did this. And I started off by solving for x as the first stage. Okay, so I'm doing this in 2 parts this way. So let me just rewrite that up here. So 12.8 equals 4 times x to the 8, really. And I'm just trying to find out what this change factor is. Step 1. Okay, divided by 4, this is, I believe, 3.2 now, and this is x to the 8. And if I take the 8th root of this, I believe it's what, 1.15 something, 6 something. Okay, I'll have to look back because I did do this. But on the calculator, how would you do that? Well, 8th root. On this calculator here, you go 8. Come on now, 8, and then you hit math, and you see how this little x, that's the 8 is going to be for the index. So 5. Okay, so 8, the 8th root of 3.2. Okay, how close was I? Oh, nice. 1.15649. 649, and so on. So you want to use as many decimal places as you can. So that's the growth rate. So every change, it grows by 1.156 times as big, okay? Every time. And so that after 8 times of this change, you get 12.8. All right. Now the question says, here's the question now. What's the doubling time? Okay. Doubling time. Well, this 8 I put as hours. Those are hours, okay? Hours. So I'm going to try and find out how many hours. Okay? So I need to do this. I need to do doubling time. Oh, okay. So if I start off with 4 grams, I want to know when I get to 8, what's the time involved? So I start with 4. I want to end with 8. My change factor is this right here, 1.15649. And I want to find out how many hours. You can do whatever you want, h. How many hours that's going to take. Okay. Now this is a little bit different, again, like I say, than the solution manual. If you ever see the solution manual, it's a little different. But this works for me, and I like this actually. It's pretty straightforward to me. So what are we going to do? We're going to divide by 4. We're going to have 2 equals 1.15649 to the power of h. And basically you're saying, you know, you're going to multiply this by itself how many times before you get to 2. So 1.15 times 1.15 times 1.15. How many times? Until you can equal 2. So, of course, how do I get this out of the exponent position? Well, this whole chapter has been about logarithms. So I have log of 2 equals, this is a log now, and this power can come down in front. So at this point, you might be really fast, and you're going to do a couple steps at a time, like this. And you're going to realize that you have to divide by log of 1.15649, so on, both sides. 1.1564, and so on. And you want to keep as many decimal places as you can so you get an accurate answer, right? So that's gone, that's gone. H equals, and I believe, here I'm just going to pop over to where I did this before. Yeah. So H, and I did N before, but the time is 4.767 hours. Okay. 4.76 or 67? 4. Oh, gee whiz. Okay. So 4.767, or around to the nearest tenth. It says nearest tenth of an hour, see? So 4.8 hours. Okay? 4.767, or 4.8 hours. Okay, to double. So it took 8 hours from 4 to grow to 12. It takes 4.8 hours for 4 to grow to 8. That makes sense, doesn't it? All right. Okay, so that's the practice that I've got for you. I think that's kind of all the ones that I plucked out there. Again, this 7D, I'll let you take a quick look at 7D. It's a bit of a mess, a bit of a monster here. But yeah, you're using logs, and it actually involves the change of base formula, which honestly is a bit maybe more than you need to know probably for this test. I did this with a calculus student just yesterday, to tell you the truth. I went over a question just like this with. So we'll deal with this maybe in calculus a little bit more, but that's your 7D. Okay? All right. Good luck in your studying, and I hope things go well for you.